if e to the mx is a solution to your differential equation, then we should be able to take a couple of derivatives, put it back into the differential equation, and see what we get, right? So if we have e to the mx, and then we have, what's the derivative of e to the mx? M e to the mx. And what's the derivative of that? M squared e to the mx, right? So the idea is we want to put those expressions into the differential equation. And what happens when you put all that stuff in there? We'll take the double prime, we'll take the prime, and then we'll take the original, and then we want this to be equal to 0, right? So what can we do here in this equation? We can what? Factor out. What are we going to factor out? We'll factor out an e to the mx. So this is gone. This is gone. And this is gone. Hey, look at that. This is, what is this? So e to the mx will never be equal to 0, and we have a quadratic equation. And how would we solve for that? Just factor, can't we? M plus 2, m plus 1 equals 0. So m equals -2 and -1. Now, if I was asking for a solution to the differential equation, would this be your final answer? You solve for x. So yeah, we plug in the m's. So remember that our solution is supposed to be this. So we have solutions. So we have y equals e to the minus 2x. And y equals e to the minus x. Is that right? Yeah. Oh. Yeah, if m is equal to 0, e to the 0 is 1, and so that's not a solution. Yeah, so that's not going to get us. In fact, e to the mx will never be equal to 0, so that's a good thing to remember when you're solving for these things. So it's a quadratic, so we should have 2 solutions, and here's our 2 solutions. In terms of the differential equations, we have 2 solutions, and I think if I put each one of these back into the differential equation, I'm going to get it to work. So I think I'm pretty convinced that these 2 are solutions to our differential equations. But what should we consider? What are the couple of things that we need to consider here? We have a second order differential equation. So remember last time our discussion was about fundamental solutions. Do you remember fundamental solutions? What's a fundamental solution set for your higher order differential equation, say? You remember what it says? So the fundamental solution set is going to be a set of solutions to your differential equation, right? There's a couple of things that has to happen. First, the fundamental solution the number of solutions you have should match the degree of the order of the differential equation. Okay? Does that statement make sense? So we are building a fundamental solution, and this is a second order differential equation, so I have to have two solutions. Okay? So second order differential equation, looking for two solutions. Let's make a note of that. And the fundamental solutions also has to be linearly independent. Now, I can tell you now that these two are linearly independent, because if you're to do, how do you check linearly independent again for functions? What's that mechanism called? What's that matrix? Determinant of some matrix that we have to find? No. The what? The Wronskian. You guys don't remember that? It wasn't that long ago. Like 5 days ago. The Wronskian. Did you guys, anybody show up to Epic yesterday? Yes, me was probably sitting in a room all by herself waiting for somebody to come by. Maybe I should give you your test back and then make you go to Epic. I don't have your test graded yet, so I don't know. Sorry. But if you get a bad grade, that would get you to go, right? That shouldn't be the motivation. You should just go. All right, so we need two linearly independent solutions for a second order differential equation, and we have found it. So usually we would denote it as y1 and y2. So let's put y1 and y2. I was going to make this into a quiz today, by the way, like a little pop quiz. I thought I'd just call it a warm-up. All right. So if I were to ask you what the general solution was, remember what happens with the fundamental solutions. Fundamental solution is just a collection of functions that would solve the differential equation. If I were to ask you for the general solution, what would the general solution be? What? Just y2? Now? Do we do a plus c? Does anybody remember? Let's look at our notes from last time. There should be something about the notes from last time, right? Yeah. It's the addition of all solutions. Not only that, but the linear combinations of all the solutions. So if C1, C2, all the way up to Cn are fundamental solutions, then your general solution would be the linear combination of those linearly independent solutions. And the plus C, instead of a plus C, you actually have the arbitrary constants from the linear combinations to be your arbitrary constants. So your general solution is C1 times e to the negative 2x plus another constant C2 times e to the negative x. And that is your general solution. highlighted in red, but of course you guys can't see red on the screen. You will if you look at the notes. Okay? That seems kind of fun. So you need two solutions, and then the two solutions will make up your fundamental solutions, and then the general solution would just be the sum of those solutions with constants in front of it. And that's it. That was what we learned last time. Remember? Did anybody get to the second one? That was one solution, right? Let's do the second one real quick. So mx if mx is a solution, then I'll need all these piece of information and say, hey, we're going to be doing the same thing over and over again, right? We're going to use this thing, and then we're going to come up with a quadratic. So let me just copy and paste things and change them. So when you get things like this that look like the same things going to happen over and over again, we give it a name. So eventually, by the end of this class, we'll see what the name is for this quadratic equation that we're getting here. All right, so we got m is equal to, what's the solution here? M is equal to -1 with multiplicity 2. So in other words, the theory behind the quadratic equations is that you need two solutions. So you're going to get two solutions here. And the two solutions happen to be the same. Yeah. What? I mean, m equals -1 is a solution, and then the other solution is m equals to -1 again. So this is m plus 1 quantity squared. And so that's what multiplicity for quadratic equations mean. All right. So it looks like a solution. I have to say that one solution is going to be y equals e to the -x. Now we have an issue here because this is a second order differential equation, and according to the theory, our fundamental solution needs to have two solutions. We have one, so we need to find another one. And if e to the -x is another solution, that's the same as that, which means it's linearly dependent. And so that's not going to work. So if you say y equals e to the -x is another solution, then these two are not linearly independent. So we have to cross that out. Oops, that's too much crossing out. Let's just delete it. So we only have one solution. We need another one. Yeah. We could. I don't know if that's going to help. So we go to section 4.2. So section 4.2 tells us that if we have a solution to a differential equation and we want to find another solution, which somehow is eluding us at this point, then we can do this thing called the reduction of order. And the reduction of order says that if you have one solution, then your second solution is just going to be the first solution times some unknown function, which we will find, some unknown function. And so if we do the substitution, we're going to get a differential equation with a u in it. and then it's all going to work out. I don't know. I hope. Let's check it. Okay, so this is the theory behind the reduction of order. Somehow, when you do the substitution, somehow your order is going to reduce from a second order differential equation to a first order differential equation, which we should be able to handle, right? Because we're first order differential equation specialists now. At least if you pass the test, that means you know how to find solutions to first order differential equations. Did you guys pass the test? I don't know. I haven't graded it yet. All right, let's take a look at our problem. What was our problem again? This is our problem. And we know that e to the negative x is a solution. All right. So let's say we have a differential equation and we have one solution. Let's see if we can find the other solution that's linearly independent so that we can create a fundamental solution set so that we can give our general solution. That's the process. All right, we're going to let, what did they say? We're going to let y is supposed to be a solution where u of x, y is equal to u of x times y1 of x. So we want that to be a solution. So let's see, say that again. That's y is equal to u times e to the negative x. So let me drop the parentheses x notation and just look at it like this. So what do I need for y? I need the first derivative and the second derivative. So let's take some derivatives here. Y prime is equal to, now u is a function of x, although I dropped the parentheses x there, but we have to assume that u is a function of x. And so we need to do that product rule, right? So u prime, derivative of the first times the second, plus the first times the derivative of the second. So we have y prime. Y double prime is going to be derivative of the first times the second plus the first times the derivative of the second plus do the same thing over here. Derivative of the first times the second plus the first times the derivative of the second. So there's well, the second here has a negative. Derivative of that is going to be a positive. Is that okay? Did I do that right? Just for the sake of putting it back into this differential equation, let's do some simplifying. I should have done this y double or y prime is equal to u prime e to the negative x minus u e to the negative x. And then meanwhile, this y double prime is equal to u double prime e to the negative x. And it looks like I have two of them here, minus 2 u prime e to the negative x plus u e to the negative x. Wow, that looks like a big mess. Let's see what happens. Let's put that in all into here. So y double prime is going to be u double prime e to the negative x minus 2 u prime e to the negative x plus u e to the negative x. So that's y prime, or y double prime. Y prime is up here. That's u prime e to the negative x minus u e to the negative x. And then y is just e, or u times e to the negative x. Got all the components here. Yeah, there's some stuff that we can factor out. So this is y double prime, y prime, and y. We can definitely do that. Yeah, let's see. E to the negative x, factored out. What do we have left? We have u double prime minus 2 u prime plus u plus 2 u prime minus 2 u plus u. Is that right? Does that look right? I just took out e to the negative x. Any algebra errors there? Okay, let's see if we could do some combining. Can we combine? What do we have? They all cancel. Is that right? So it's just u double prime? Wow. Hmm. Well, this is supposed to be a reduction of order because the idea was that we're supposed to let w equal to u prime, but we kind of don't need that since this is a simple case. So w prime is equal to 0. So what's the antiderivative of w? Or I guess what's the antiderivative of 0? What? That's a constant, right? Because the derivative of constant is 0. So this is kind of lame, but chances are you're going to have a u double prime plus something with a u prime in it. And there's no more u's. The u's are pretty much guaranteed to cancel. And so with the u's cancel, you have a u double prime and a u prime, and that's when you do the reduction of order where you use the w. But in this particular scenario, it just came up to be really simple. Anyways, we want to eventually solve for u. So w is equal to u prime, which means u prime is equal to some constant. So what does u equal to? C times x, right? some constant times x. So that constant times x, actually a constant doesn't mean much, but the x is the function that we're looking for. So then if we go back to our original substitution here, y is equal to constant times x times y1. So this is going to be constant times x times e to the negative x. That's our second solution. So this is our second solution to our fundamental solution set. Yeah. Yeah, but the plus c happens automatically. No, let's just, yeah, forget about it. In fact, this plus c, or the c constant over here, I ended up dropping it because c times x times e to the negative x is linearly dependent with x times e to the negative x. And so if I'm looking for a basic fundamental solution, let c equal to 1. Now, the first time we see this, we should not believe it, and we should actually check that this is, in fact, the solution. So let's check that this is a solution to the differential equation as they claim. So this says check that y2 is a solution. So what do we need? Y2 is equal to x e to the negative x. We need the derivative. Y2 prime is equal to derivative of the first times the second plus the first times the derivative of the second. And y2 double prime is the derivative of that. And then we end up with a product rule here. So it's the first times the derivative of the second plus the first times the derivative of the first plus the second times the second plus the first times the derivative of the second. And the derivative of the second has a negative sign, so that's why there's a negative sign. So this becomes minus 2e to the negative x plus x e to the negative x. So if I plug that into the differential equation, we should get 0. So minus 2e to the negative x plus x e to the negative x. So that's double prime plus 2 times the prime plus 1 times the original. What's this equal to? We got negative 2e to the negative x plus x e to the negative x plus 2e to the negative x minus 2x e to the negative x plus x e to the negative x. So we got the x e to the negative x's all cancel out, and then we just have the regular e to the negative x's also canceling out. So this is equal to 0. Now we have our second fundamental solution, and we can finally write our general solution. So general solution is going to be C1. What was the first solution that we got? Just e to the negative x plus C2. And then what's our second solution? X e to the negative x. Okay? That's not so bad. Now, if we take our first example in our warm-up and say we just found one solution instead of two, if we take our first solution and just say e to the negative 2x is a solution that we got, and say we didn't know that this was a solution, what you could do is you can use a reduction of order on this solution with this differential equation, and then somehow you're going to come up with e to the negative x as the second solution after you simplify things. Okay, so that's how it'll work. We did this for a specific example, but you can do this more generally. And if you do this more generally, you will end up with a formula that you can use instead of going through the process of, taking derivatives and stuff like that. But in general, well, let's see. Long. Pasting. So I don't want to go through the step-by-step process here. This is outlined in the book, but you assume that u times y1 is a solution, and then you take a couple of derivatives, and then you put that back into the equation, and then you're going to come up with a separable differential equation, etc. But the point is that your u is going to equal to some integral of something. Okay, so let's just use this formula to verify our first warm-up problem. So let's say our problem was given, that warm-up problem, y double prime, what was it? Plus, what? 3y prime plus 2y is equal to 0. And then you guys found, let's just use one of the solutions. And it really doesn't matter which one we found. Let's say we found one, only one. Let's say e to the negative 2x was a solution. And let's see how we can use this formula to find our second solution. What's p? We need to know what p is. Backtrack, backtrack, backtrack. P looks like it's going to be the coefficient of the prime. And then q is the coefficient of the y. although we didn't use Q here. So let's say P is equal to, in our problem, is equal to the coefficient of the y prime, so that's 3. Okay? And we are interested in finding u so that we can multiply it with our y1. So u is equal to the integral of e to the negative the integral of p dx divided by e to the negative 2x. That's y1 squared dx. I don't know if you want to use this formula, but if you can handle using this formula, then this is just a formula to use. If you don't want to use this formula, then you would have to go through the whole process, which might be easier. I don't know if this formula looks confusing. All right, so we need to figure out, let's go through this step by step. I think the first thing we need to figure out is this. This is going to be 3x. And the constants, the plus c's, let's not do the plus c's until the very end. So this will be a negative. So we're really integrating integral of e to the negative 3x divided by e to the negative 4x. Is that right? dx. We can simplify this, can't we? What is this? Negative 3 minus negative 4. Positive x, e to the x. Oh, that's just equal to e to the x. Look at that. And remember, let's not worry about the plus c. So that's what u is equal to. So y2 is equal to u times y1. So that's e to the x times e to the negative 2x, which is equal to, hey, that was the same function that we had earlier. Yay, it works. That's cool. Or not. But it could be cool if you like it. Okay. So this is good for second order differential equations. And that process that we did is good for second order differential equations with constant coefficients. But we can extend that to higher order differential equations because it seems like we're just solving for things. Okay? Trust me, it's really cool if you understand it. Maybe it's not cool right now because yeah, the plus c's, if we put the plus c's there and then we mix it together with our general solutions, it'll all end up to be plus c's as coefficients. So we generally, in the middle of our work, we don't put the plus c's anymore. And the plus c, in fact, it doesn't become a plus c, it becomes times c. Yeah. So again, if we have the first solution and the second solution, then our general solution is going to be y is equal to, oops, it looks like a negative, c1 e to the negative 2x plus c2 e to the negative x. And so those are where the arbitrary constants go. Ramsey? It should work with anything. Like if your first solution was like an x squared, then you should be able to go through the process to find your second one. Okay? So maybe we might take a look at this later when we come up to another problem where we have, we don't have our second solution. Okay? Any other questions? That's the reduction of order. So now let's jump into our next section, which is actually solving for second order differential or higher order differential equations with constant coefficients. And this basically is what you guys did on your own. Except we'll try to capture the more general essence of what you guys were doing. So a differential equation, a second order or maybe even a higher order differential equation with constant coefficients has solutions of the form e to the mx. And so for second order differential equations, we can just write that as e to the mx. Take the derivative twice, you get m squared. Take the derivative once, you get m. And if you put that into the differential equation, what you're going to end up with is this quadratic. And if you set that equal to 0, you have a quadratic equation. Do you remember what happens with a quadratic equation? What are your possibilities for your solutions? There's 3 possibilities, I think. One of them is our first issue where we got 2 distinct real roots, right? Second one is our second there where we got 1 real root that's repeated, multiplicity 2. What's our third case? So no real roots. Why would we have no real roots when you use a quadratic formula? Somewhere along the line, we put stuff into the quadratic formula and we run into something and we say, okay, we have to stop here because there's no real roots. Do you guys remember what the quadratic formula is? Negative b plus or minus the square root of 4a. What? Something like that? So where, at some point, do you stop and say, there's no real roots, there's no solution? That thing inside of the square root, right? When that thing inside of the square root is negative. So if b squared minus 4ac is positive, then we get 2 real roots. If b squared minus 4ac is equal to 0, it turns out that we're going to have 1 repeated root. And if b squared minus 4ac is less than 0, then we actually have something there. Anybody know what we have? Imaginary numbers. We actually get complex conjugates. That's some crappy writing right there. Why don't I just do the 2 cases? let's summarize the two cases here on this page, and then we'll take a look at the third case in the next page. So the first case, when b squared minus 4ac is bigger than 0, we have two distinct real roots, and we can see that we're going to have two fundamental solutions. And so the general solution is just going to be a linear combination of those fundamental solutions. When you only have one real root, then by the reduction of order, and this is always going to happen with these types of problems, and I want to stress the fact that I'm saying these types of problems because when you're having another type of problem that's not second order with constant coefficients, then there's something different that we have to do. But with these types of problems, the second order linear constant coefficient problems, your second solution is always going to be x times the first solution for the repeated roots. Now for the third solution, we have imaginary numbers. Should I just copy my notes or should I write it down? I want to write it down because it's exciting to me. But when I write it down, it's hard to read. Just copy it. It's not that exciting. It is, really. Yeah. No, we're in the real world here. And so what happens when we're finding solutions is that we're going to briefly go into the complex world, do stuff there, and then we're going to need to bring it back to the real world. And so our answer is going to be reals. All right. Before we get started with this, with finding solutions, I need to tell you this cool formula called Euler's formula. Have you guys heard of Euler's formula? There's too many. Euler has all kinds of formulas. Let's Google Euler. I only have 10 minutes here. I don't know if I should be doing this. There's like too many of them. So your answer is supposed to be e to the whatever the root is. And if your root has a complex number, an imaginary number I, we're going to have to use Euler's formula. Look at that. Isn't that cool? Now when x is equal to pi, this becomes a cool formula that has e, that has pi, that has I, that has 1, and that has 0. And so it has all those special numbers in math that people end up getting tattoos of that formula. Seriously. E to the pi I plus 1 is equal to 0. Sine of pi is equal to 0. Cosine of pi is equal to -1. Bring the -1 over to the other side. And so you got the additive identity, the multiplicative identity, the pi, the circle thing, the e, the logarithmic exponential thing. So those are all special numbers. Anyways, I'm just temporarily basking in its glory. So, what do we really want to do here? We really want to just find solutions. And so I'm just going to, why don't I just copy and paste my notes. Oops, what happened? I was afraid something weird's going to happen. All right. So if your solution is some complex number, then it's a complex conjugate. This is all look confusing? Yeah, okay. Let me just write it out. Maybe we could do an actual example. What? X equals pi? No, let's come up with an actual differential equation. So let's see if we have this differential equation that looks like this, and I'm going for the easiest type of differential equation. Then we say y is equal to e to the mx is our problem, right? And then we would get that y prime is equal to m e to the mx, y double prime is equal to the m squared e to the mx. Actually, after you do this a few times, you'll see the same pattern, and then this will just be m squared e to the mx plus 4 e to the mx is equal to 0, e to the mx factors, m squared plus 4 is equal to 0, and then m is equal to plus or minus 2i, right? So that's our complex conjugates. Complex conjugates, by the way, are like something plus something I, the same something minus the same something I. Those are the two complex numbers that we get. So technically it's 0 plus 2i and 0 minus 2i. So those are the complex conjugate solutions that we come up with. Now, what we need to do is we need to continue working with this, what it means to be e to the negative 2i. Or positive 2i. I guess it doesn't matter. And according to Euler's formula, this is equal to cosine of 2, oops, m. This is m, so I need to say m times x. So 2i times x, right? So 2i times x, so this is equivalent to saying cosine of 2x plus I sine of 2x. Actually, it might be better if we write this as e to the 2x times I, and then it would look kind of match Euler's formula a little bit better. So, and then the other solution, e to the minus 2i times x is equal to cosine 2x minus I sine 2x. So we have a couple of issues here. First of all, we want our solutions to be real solutions. Second of all, the combination of cosine 2x and sine 2x looks like it might be enough for us to make a fundamental solution set. Okay, so remember, our main goal here is to find a fundamental solution set. And if we take a look at the cosine of 2x as one solution and the sine of 2x as the other solution, I think that's enough to cover our basis. Now, first of all, we should check that if we take derivatives of this, that it would satisfy our differential equation, right? So let's quickly do that. So we need a couple of derivatives, y1 prime. The derivative of cosine is negative sine, right? Negative 2 sine 2x. y1 double prime is the derivative of sine is positive cosine, so negative 4 cosine 2x. And we'll put that into the differential equation. Minus 4 cosine 2x plus 4 times the original cosine 2x. And that, in fact, is equal to 0. So put back into the differential equation, it works. And we'll do the same for the other one, and we'll see that we'll get the same results. We got y2 prime is equal to cosine 2x times 2, and y2 double prime is equal to sine 2x negative 2 times 2 is 4. So we get minus 4 sine 2x plus 4 times sine 2x, and that's equal to 0 as well. So now we've got it verified. We have two, and these two happen to be linearly independent solutions. So this makes our fundamental set. And so our general solution then this is supposed to be in red. C1 cosine 2x plus C2 sine 2x. Okay. So now that we have this example, I can just copy and paste my notes for the general term. And let's walk through it. So my example had a 0 plus something I. And if that term is not 0, then we have to make sure that we account for that. So the most general conjugate that you would get from the quadratic formula is you have something plus or minus something I. And so according to Euler's formula, because our something had a 0 real part, our complex conjugate has 0 real part, we have e to the 0, which we just ignored. But in general, if you have something there that you would keep an e to the alpha times x, whatever that alpha is. And then what you come up with is that your first fundamental solution would be the cosine of that thing next to the I times x. And then your second would be the sine of that thing next to the I times x. Okay? So, oh, is that cool or what? No. Okay. Try to walk through the theory, look through the notes, try doing the problems, and then we'll do a few of these. Once we do a few of these, then we'll get used to them. Okay. So I'll give you guys a quiz on Thursday that had some of these problems. Good luck. It'll be generally 4.3. Okay.